Okay, so I'm going to just do the example. I'm going to change the question. I'm going to define graph. Consider the graph f of x is equal to x squared minus 4, and g of x is equal to negative, or g of x is equal to x minus 2. Now I'm going to graph h of x is equal to f of x times g of x. Changed it up. So very simply, I'm just going to get x values, and I've added a couple of more of negative 3 and 3. Figured out the f of those x values. I looked at the graph, pulled that out. And g of x, I've also looked at the graph and pulled those x values out. So I've got the x values. For specific x values, I found f of x and g of x. And to get h of x, I'm just going to simply multiply them. Now, I'm going to ask you, perhaps, if we are multiplying a quadratic, degree 2, with a linear function, degree 1, what would you expect the outcome to be? Well, we should see a cubic. Degree 1 times degree 2 multiplies to degree 3, which is cubic. So I'm just going to maybe write down my x values, or my points. I know I have a point on h of x as negative 3, negative 25. Right, negative 3, negative 25. And then 2, comma 0. And then negative 1, 9. 0, 8, 1, 3, 0, 0. Last, 3, 5. So I'm just going to plot those points along. Now, at any point, you could take, for instance, those two integer numbers, or the y values, they're integers, you could multiply them. Negative 5 times negative 5 is negative 25, which is way down there. Or you could simply look at my table. For x is equal to negative 2, you had a y value for f of negative 2 is 0. The g of negative 2 is negative 4. 0 times negative 4 is going to be 0. So I have a function that it looks like this so far. And then negative 1. So what I notice is my y values for both functions is negative 3. So negative 3 times negative 3 is positive 9. Well, that's interesting. So that goes all the way up to positive 9. And 0, right? So the f of 0 is negative 4. The g of 0 is negative 2. Negative 2 times negative 4 is positive 8. Don't get confused. That is positive, right? Oh, wow, this function turns around. And then I can do the same for for 1. And what we see is you get a y value of 3. I can do the same for, this should be x is 2. When x is 2, the f of 2 and g of 2 are both 0. 0 times 0 is 0. And 3, when x is 3, the f of 3 is 5, and the g of 3 is 1. So I get there. And in fact, I see a cubic function. Let's go on to the next example. Hopefully there was no surprises. What is your first instinct here? If we're going to have h of x is equal to g of x divided by f of x, we're going to determine the equation of h of x. And h of x is going to be g of x divided by f of x. Now my h of x is going to be my g of x, which is really 3x plus 9. And my f of x, now if I look at f of x, it's defined by x squared plus x minus 6. it's always a good strategy to try to factor out or factor any expression you have, just in case something nice happens. And I factor out the denominator first. I don't know, just instinct tells me to do that. And then I'm able to factor out a common factor from the numerator. And what we should see is h of x cannot be equal to, x cannot be equal to negative 3 or 2. So there's my non-permissible values. And what we're probably noticing, you're probably yelling at the screen, is that you can cross out a common factor of x plus 3 from the numerator and the denominator. And just like the previous problem where you're multiplying two quadratic expressions, you end up in a polynomial in one unit. Here, what's going to happen is that when we take a function and we divide it, what happens is that, in fact, out comes a rational function. All right. So, dealer's choice, you know how to graph this. You could graph this by graphing f of x and g of x, and then just taking the y values of the g divided by the y values of the f for each x value, or you could simply jump to a different unit and graph this. What we should see, though, we have a horizontal asymptote of y is equal to 0. That is because the degree of the numerator is less than the degree of the denominator. Under that condition, we have a horizontal asymptote of y is equal to 0. We have a vertical asymptote whenever our denominator is equal to 0. So here, that is when x is equal to 0. Now always keep in mind we have non-permissible values. So I have a vertical asymptote at x is equal to 2. There we have it, horizontal asymptote at y is equal to 0. And I can simply graph this with a table of values. Just like in previous units. Anyways, I won't bore you with the details, and I'm just going through the motions here. So that would be positive infinity when x is equal to 2.01. When x is equal to 3, we have a y value of 3. When x is equal to 6, we would have 3/4. And essentially, I'm just taking my y values. Remember that my vertical asymptote splits up my graph into two different sections, essentially. And I'm taking a look what it looks like at the right, and I am almost pulling like arbitrary values for x here, and I'm just going to plot them down. Or, I mean, there's so many different ways that you can graph this. You can even graph this using transformations, couldn't you? And that would be my graph. And I take a log and make sure that everything's okay. Everything's not okay, because don't forget my non-permissible values. So I have to put a hole in my graph. And the hole in my graph that I'm going to put is at -3. Let's make this very obvious to the person who's ever marking it. There we have it. My domain of my graph is going to be x such that x is element of the reals, but x cannot be equal to -3 or 2. My range is going to be y exists such that y is element of the reals, y cannot be equal to 0.